Good. All right. So this is the last class, and just want to point out the news. There's a lot of exciting news. There's another series of vulnerabilities in Intel. This is like Spectre and Meltdown. It's a similar attack. And they have cute logos and cute names for them. And this is what was predicted. When they found the Spectre and Meltdown flaws, the problem is the secret areas of the chip share resources with the other area, and you can leak out secrets with cache timing. And this is worse, of course, if you use hyperthreading, where one core switches from one process to another, sharing resources, and again, giving the possibility of side channel attacks. So there's another series of these vulnerabilities and another bunch of patches coming out. And here's another one. This is the vulnerability in Cisco. And as everybody has to do, vulnerabilities now get names and they get logos. So this one is named after 3 emojis, 3 angry cats. And so anyway, this one lets you bypass Cisco's trust anchor. This one's actually quite interesting technically. Cisco routers have a trust anchor, which is on a separate chip. It's the same thing as the secure element in an iPhone or the trusted platform module on a PC motherboard. It's a special cryptographic chip to hold the secrets that is not in the address space of the processor. So the idea is that no kind of malware or attack on the processor can reveal the secrets, but they control it with a floating point, a field programmable gate array. And field programmable gate arrays are supposed to be so hard to program that you can't subvert them. But these guys figured out a clever way to experiment with the field programmable gate array until they found out how to corrupt it and cause it to leak out the secrets on the secret chip. And to do this, they had to buy 4 or more routers at $10,000 each and mess with them until they destroyed 2 of them. So it's not easy or cheap, but they were able to overcome the security and break into the secure device. So this is not a very practical attack. You have to have root on the router. The interesting thing is not really that it's going to take over the routers on the internet en masse, but that it shows yet another flaw where this supposedly secure element is not really perfectly secure. And there's a variety of attacks to go against each of them. It is a good place to hide your secrets, but it's not perfect, of course, just like everything else. Now people are getting mad because the iPhone is so secure. You know, in my mobile device hacking class, we pretty much skipped the iPhones this semester because I have the same problem. I can't really get into the iPhone, although now there is a jailbreak for iOS 11. So next time I teach it, I'm going to have some jailbreak devices available in the cloud. But anyway, now people are complaining there's a WhatsApp flaw, a 0-day used against us in a targeted way against a small number of activists. And again, not something that normal people probably have to worry about, but it does show one of the issues. You can't put any virus on your iPhone, and you can't tell if your iPhone is hacked because you can't mess with the operating system from the outside. So people are complaining about this. I'm not sure what they want. If they open up the iPhone like Android, there'll be a ton of malware like Android. But anyway, it is, of course, an issue that it is locked down and nobody can get in there. And that means even the good guys can't get in there to find out what's going on. So you pretty much, I don't know how you have one of those things without the other. So this leaked out in the Mueller report, and there were rumors of it before. The Russians attacked United States voting systems, and they did penetrate 2 districts in Florida to some extent. And all we ever get is a few words and then a bunch of evasion and concealment. And now these guys are claiming that the FBI made them sign a non-disclosure agreement, and it's the FBI's fault. They can't talk about it. That sounds pretty bogus and fishy to me, but who knows? Anyway, now they're saying 2 districts were penetrated into the voter registration rolls, but they didn't get to where they could actually change the votes. I don't know what to make of this. I highly suspect we're not getting the whole story. Anyway, here's another platform for quantum computing, which we're going to be talking about today. We'll talk about the 2 main platforms, but here's the third one. You have a chain of atoms, and then you have an energy or a light bit of energy, in this case a photon, and it spreads out down the chain. This is another quantum system that you can use in principle to do quantum mechanics mechanical computations. This is very theoretical and not really working yet, but that may get us somewhere. One thing about this is it might work at room temperature, which is really important. All the other quantum mechanics computing systems I know have to be cooled to ridiculously low temperatures, and that makes them very expensive. Hey, I haven't got the video going because nobody was here. Just a moment while I started. You're the only physical attendee, and I forgot to turn on the video. That's fine. All right. High-tech remote. High-tech remote. There we go. All right. Good. All right, so that will hopefully come up. And yeah, that one's not that exciting. This one is the one I thought was very interesting. Let me see if I'm going to get video. I do, good. So I've seen these things on the buses in San Francisco for last month to Gemini, and today at some cryptocurrency conference, they announced Flexa. This is a Winklevoss product. The Winklevoss twins that were mocked ruthlessly in the Social Network movie have created this spend app that is spend spelled wrong, and I couldn't believe it when I went here. This is the spend webpage. And notice something about it. It's 5 pages wide and has a little spend over there. I looked at, this is in CSS. It is 9,999 pixels wide for no apparent reason. I wonder if they did this deliberately. I kind of doubt it. Anyway, this thing is in iPhone form only. There is no Android app. And the Winklevoss twins, one of them, the CEO of the company, has issued a statement that's sort of strangely badly misspelled. And, you know, it really seems to me like so many other cryptocurrency things, it's bogus. It's highly bogus. It's not really ready for anything. They got a bunch of big names on it. Supposedly Whole Foods will let you pay with Bitcoin. And the reason for this to exist is the same old tired thing I've been hearing for years, that you're going to save the credit card processing fee, which I really think makes no sense at all. Bitcoin has a fee too. Everybody has a fee. I don't understand what vendors will get out of it or what customers will get out of it. And I think all it is another scam where they got somebody to invest. They put a bunch of ads up. They bid a lot of hype, and then they get more investors, and then it collapses, and they pretend they couldn't see that coming. But anyway, other than that, maybe we'll all be paying for things with Bitcoin. But the thing that's completely missing is why anybody would want to do that.
Sounds like a vulnerable app waiting.
I know, and I wanted to test the vulnerability app, but there's no Android app for me to test. There's only an iPhone app, which would be connected to my real bank account. I wasn't willing to do that. And, you know, every time this happens, I go try to look at the blockchain. I couldn't find any details. Try to look at the app. I couldn't find any details. And I've been here before. The last one I noticed like this was Lisk. Lisk, the day before it launched, I tried to download the software and the download links didn't work. The documentation pages weren't there. And I'm like, what is this garbage? And it was garbage. This is cryptocurrency. You put up an empty box with a pretty sticker on it, and you get people to invest. That's the entire product. Actually making anything is of no importance. It's just putting on the show of something and getting the investing money. That's
you can't even make a pretty sticker. How do you expect somebody to trust you to make a working app?
Yep. Well, that's why the only thing that matters is the appearance, and that's because it's a scam, I suspect. But I can't prove that, of course, because I can't get the details to prove it. Anyway, let's talk about quantum mechanics, which is, of course, near and dear to my heart. I did my thesis on quantum mechanics, and I think it's great to see this stuff coming by and becoming more useful. So we'll talk about how quantum computers work. All right. So, and here I think it's good to just review what's going on with normal computers, because I think in the modern world, people don't start from the hardware. So this is how it all started with digital computers. You'd have these diodes and wires that are like 0 or 5 volts, and then you have these gates. There's a NOT gate where you feed in a 0 and it turns it to 1, or you feed in a 1 and it turns it to 0. So this is the truth table. A comes in and Q comes out. Then you have an AND gate that combines 2 objects. So if they're both 1, you get 1, but otherwise you get 0. And then you have an XOR. So if they are different, the answer is 1, and if they are the same, the answer is 0. These are the fundamental logical operations, and all you do is combine them in large numbers to add up to every other mathematical operation. And that's what digital computers do. So here's what you have to do to make a digital adder that will add these 2 bits, and then if necessary, send a carry bit over here and add these 2 bits and send a carry bit over here. So you can make any number of these things. With just a bunch of these little components, you can build any process you want. Now, the problem is real devices are not digital. The real world is analog. So the actual voltage in your circuits is like this. It varies continuously from one place to another. So what you do is you design circuits with diodes that will clip the maximum minimum voltage, and then you put amplification to accelerate this to try to make sure that it spends most of its time in the region you call 1 or in the region you call 0, and it has a minimum amount of chance of being in the forbidden zone, which is something that is not 1 or 0. So what you do is you have hardware that is analog, and you design it to change it into digital. And you ignore all these subtleties and just call this 1 and call that 0. So you get very little benefit from real hardware. You coerce the hardware into pretending it's digital when it wasn't. And since it has some chance of being wrong, you have to have error correction. So you have some kind of system where you take some combination of the bits every now and then and make a correction byte or something, and you check that mathematically so you find out when there are errors and fix them. And that's what we're using for digital computing. So let's talk about analog computing. Analog computing was first. This thing is from 100 BC. This was like a device you would use to plot out the motions of the stars and planets. You would just turn something and this thing would simulate it. That's one of them. And then there's a slide rule. Slide rule was a way to do math before we had pocket calculators. You have rows of numbers here, and they are logarithmically spaced. So you can multiply 2 numbers by adding the numbers in logarithms here. And you can divide numbers by subtracting. So you can do multiplication. This is a 4-function calculator. You can do adding, subtracting, multiplying, dividing with no power in an analog way. And the precision is determined by how precisely you can place this little pointer. So if you are careful, you can place it to perhaps 1/10 of a millimeter. And so now you can talk about how many bits does this process. It's an analog device, but it has a limited precision. And what most people say is you can get about 3 decimal places out of these things. So that's about 10 bits. My father had one that was a circular platter the size of a record that went around and around like a spiral. So the total length was 30 feet. And he claimed he could get 5 places of precision out of that thing. And so that would be like 16 or 17 bits. So you can quantify it in terms of bits, but it is not a digital device. It does not have bits, but it does math. And then you got this. This is an analog computer. If you have a flute, all you do is blow against a wedge, so you create white noise. And the flute is designed so that the motion of the air inside the flute causes certain wavelengths to amplify and other wavelengths to cancel out. So it turns into a note. So that's what's called the Fourier Transform. This is an analog computer calculating Fourier Transform. It is taking white noise and breaking it into the frequency components and changing the output based on those frequency components. So now you can talk about how many bits does it process. It's not digital, but in fact, we all know this. This is the problem with the internet and all digital. If you want to take that music and record it, what MP3 files do is they take 20 or 40,000 samples per second, and each sample is about 24 bits. So that ends up to be about 50 megabytes to make a 3-minute song. And that's a measure of how many bits it takes to record this on a digital computer. But in the early days, it was all just done with analog. You would play this thing into an analog microphone that would press it with an analog thing onto a plastic record, and that you play that with an analog device. There's no digital part anywhere. You can record stuff and you can play it back, but you have a certain amount of error and a certain amount of precision, and things kind of wear out. There's a noise level, but there's no digital part at all. So those are the 2 general modes of computing. The early original plan was these analog things, which were not completely precise. And then we switched to these digital things. And the miracle of the digital things is you can actually measure how accurate it is, and you can make a copy. You can do an error correction or an MD5 hash and prove that the copy is 100% as good as the original. Whereas with these analog devices, you have some distortion every time you copy it, and you don't really know how much that is. So that's the game. So in quantum mechanics, we are not going to use bits. We're going to use these qubits that we talked about. So each qubit is not just 0 or 1. It's in a state which is somewhere on this block sphere. So it's actually not just one bit. It is a two-parameter continuously varying number. You can express it as theta and phi here, or you can express it as a complex number where you have the real and imaginary part. But in either case, you have two floating point numbers for the state of one qubit instead of one bit. So there's a lot more possibilities in one bit here. And now, if you're not going to force this into an artificial state of 0 and 1, the way you did with the electricity, and calculate that way, you're going to leave it in its native state, you're going to have to settle for the operations you can perform on a real native state qubit. And those are not going to be like and or and not. They're going to be weird operations in the quantum realm. One of them is measurement. There's an operation called measurement, which causes it to collapse to either 0 or 1 and can't be reversed. You can only measure it once, and after that, it stops changing. So that's at the end of every calculation. So like I say, if you have 8 bits of digital, you have 256 possible states. But if you have 8 qubits, you have 256 possible values, but each one of them has a complex amplitude, which is 2 real numbers. So you have 256 complex numbers required to specify the state. So that is enormously far more information in 8 qubits than you have in 8 bits, if you actually use them the way they are, instead of trying to shove them into zones and call one zone 0 and the other 0, 1. If you actually could use them the way they are, they would move much, much more data in each calculation. And that's the point. So in digital computing, n bits contain n bits of information. N qubits contain 2 to the n complex floating point values, which is a whole lot more data required to specify the state of some qubits. So you got to take these qubits and put them in some kind of circuit of quantum gates, and then you can do measurement at the end, and now you have a quantum computer, if you can build all these pieces of hardware. So the gates are the operations, and for digital computing, it was stuff like XOR and for quantum computing, it's stuff like this: measurement once at the end, 180-degree rotation about the x-axis, so that will flip 0 to 1. But if you're in some kind of in-between state, it'll just flip it to the opposite in-between state. And then the Hadamard gate, which rotates it about this axis here, the XZ axis, so it will change Z into Y. And that will, anyway, it'll change a certain state into an uncertain state. And some uncertain states will turn into certain states. That's the point of this. This creates, does strange things that are much more complicated than a bit flip, but it changes one quantum state to another.
So
And yeah.
Like on a hardware level, how are these gates created?
I know for the kind of qubits that IBM uses, I think you just do it with a pulse of electricity, magnetic field.
Okay.
So you have the thing, it's a magnetic superconductor in a state that's partly one way and part the other, and then you expose it to a pulse, and that causes it to move some distance.
Okay, so when we were reading about it, they use electricity to put it into a state ready to be processed.
Yeah.
And then when it sends it through a gate, it uses a similar technique to do like a complete 180 rotation.
Yes. Yes, you expose it to something like a magnetic field that causes it to rotate, and you give it the right amount of time, it'll rotate by the angle you want.
Okay.
That's one way to do it. There are a lot of other ways. But you have to choose, just the same thing is true of normal computing. You have silicon and then you expose it to electrical signals to make it flip. So it's the same kind of thing.
Okay.
And if you use optical computing, then there are like prisms and lenses with the property of rotating the light.
Mm-hmm.
So you can again build something that has this effect. It's a very good question. And that's only a general answer because I haven't looked at details of how it works, but that's generally how you do it. So now we can talk about the quantum speedup. So the whole reason we care is because there are certain conditions under which this is extremely much more powerful. But the problem is, it's not a general purpose process. You have to build sort of the hardware with the right circuit of gates to do it. Anyway, of course, that was true of silicon in the early days too. That's how they did it. So here's the quantum speedup. If you want to search an unordered list of n items, if you just have a bunch of items you're looking for something, it'll take n over 2 operations on the average because you have to just try them one by one. And eventually you find it, and the odds are you'll find it about halfway through the list. So that's the searching a list. In quantum computing, you can do that in the square root of n operations using Grover's algorithm, which is much faster. And this is going to turn out to be super important. So here's Simon's problem, very similar to hash collisions. You have a function, and you're going to find an M so that if f of x, if the two hash functions match, then the inputs are related in some way by XORing with them. So this is very much like finding a hash collision. You have two equal outputs of the function, and you're trying to find the relationship between the two inputs to cause that to happen. This is not a standard hash function because a normal hash function does not have this property that for all the hash collisions, the inputs have a certain relationship. But this is close to a hash function. And that's Simon's problem. And it turns out that Simon's problem can be solved very much faster on a quantum computer. A classical computer, this is the birthday attack we talked about before. If you have a 128-bit hash, it will take 2 to the 64 guesses to find a collision, because you have a list of 2 to the 64 guesses, and there's 2 to the 128 pairs there. So there's a chance, there's likely that you'll find a match. But in quantum computers, you can actually do it in n operations, which is extremely much faster, mind-bogglingly faster. Like for MD5, this would be 2 to the 64, and the quantum computer does it in a total of 128 operations, which is mind-boggling. And so that's the point. The Simon's problem, quantum computers are very fast, and this is the circuit that does it. You just feed in Hadamard gates and then some kind of weird thing in the middle, and then more Hadamard gates. If you had these components, which we don't really, you could build something here that would solve that problem much, much faster. So then there's Shor's algorithm. Shor's algorithm is more like the flute. This will solve the discrete logarithm problem and the elliptic curve discrete logarithm problem. That will destroy everything. All public key systems are broken by this, and this is what it looks like. This is, you build this system, rotating these things and having entanglement between the bits, and with the right mixture of all this jazz, you create something that does a quantum Fourier transform, essentially. And if you feed it a number that is the product of two primes, it will, like the flute, cause the part that the divisors will be magnified and the other numbers will vanish, and you'll get the prime factors here. And you get them not by going through iterations, but just by the structure of this thing, causing the prime factors to be the one where the wave functions line up right and they come out. That's the point. That's the trick of this thing. You have to understand these weird quantum operations, which I'm not explaining in enough detail to get there. But that's that is the Shor's algorithm that was developed. And this will solve the discrete logarithm problem. So that is the one that completely destroys all public key encryption, if you had hardware to do this.
I don't really understand like what those entanglement modules did, because what it was explaining was that that qubit would read the same as the other, but this shows it being entangled like 3 times.
Yes.
So what happened
And that's a good question. I don't really understand how this can be entangled that way and this can be entangled that way. That would seem redundant to me. Yeah, 3 times. Now that you mention it, I don't understand that either.
And then the X, is that the X flip? So like you flip it 180 degrees and then you flip it back 180 degrees? Yeah,
it is kind of goofy, isn't it?
What?
Yeah, you got a good point there, and I don't understand it. This seems, I could understand. I wonder if this could be wrong.
I guess what they said in the book was if you understand it, then you don't really understand quantum.
Well, yeah, but I mean, in principle, you get it. But now that you mentioned, I didn't even look at it in that much detail, but you're right. This triple stuff makes no sense at all.
Yeah.
This seems like one would be mathematically identical. So I don't have a good answer.
I guess we can test it.
Yeah. Anyway, I'd have to read into it more. It's a very good point, and I don't have a good answer. Anyway, yeah. That's fine.
Real quick.
Yeah.
Apparently, we signed the wrong date.
Okay. All right. All right.
Thank you.
Sure. Okay. All right. Yeah. All right. Anyway, so all right. Let's talk about breaking AES. So this hash cracking thing we talked about before, searching through a list, is the same thing as breaking symmetric encryption. If you want to break AES, all you have to do is hunt through a list of 2 to the 128 keys until you find the right key. So that is, in fact, searching through an unordered list. So to crack AES 128 with 2 to the 128 in classical, you'd have to do half of all the keys, which is 2 to the 127. But in Grover's algorithm, you only have to do 2 to the 64, which moves it from impossible to possible. So AES 128 is destroyed by a quantum computer if you can do 2 to the 64 calculations on one. And however, that's as far as it goes. It does not go like the public key, where you go from an exponential to like a linear or something. It just takes the square root of the number of points. So if you use 2 to the 256, it's still unbreakable. To crack AES 256 would still take 2 to the 128 operations, even on a quantum computer, and that's too many. So AES survives, but only the longer one. All right, and so there's Grover's algorithm. That's what it looks like. And this is the one that can do it in 2 to the n over 2 calculations. So all you have to do is go to AES 256, and you have still an unbreakable symmetric cipher. So AES survives pretty well. All right, but all the public key encryptions are shot. Now the problem is building this hardware is very difficult. The fundamental problem is noise, and this was the same thing with the analog records and with the flute. If you're going to do this kind of computing, what matters is the quality of your inputs. And since you're not going to digitize it, you're actually going to take the full state of the qubit and use it, then the noise is your limit. And the noise is pretty drastic. The thermal noise really messes it up. So they have to cool these things to like a few millikelvins above absolute zero, and they're still only stable for a few milliseconds with the superconducting circuit ones. And the other technique is ion traps. And there's another one of these bogus companies, IonQ. I mean, I don't know much about them. I just know this is really hypey looking stuff. So you won't even let you see the website without asking for permission, but they will let you see this statement. They've made a commercial trapped ion quantum computer. And it's the most wonderful thing in the world. And they claim that it has 11 qubits and that it has less than 0.03% error. So that is pretty drastically horrible. I mean, I think the calculation I showed, to crack RSA, you'd need like 4,000 qubits. So even if you believe the hype, which I highly don't believe, these guys are still nowhere near it. So there is no sign of anything that can really crack real public key encryption anywhere on Earth. No one expects it in sooner than maybe 20 or 30 years. Anyway, here's another one. University of South Wales claims that they have proven accuracy in quantum computations, and I looked through several of these papers and I could not find any statement of what temperature it's at. I think they haven't even built it yet. I think all they've done is show that they could prove how accurate it was, but they did have one place where they claimed they managed to get a fidelity of 98%. That means a 2% error rate, which is horrible. I mean, people are upset about digital computers that have like 1 part per billion error. I mean, if you have a 2% error rate, that means you're going to spend most of your time error correcting. But anyway, they're proud of 98%. So we are so far from anything that would actually work. Here's another one. This quantum computer comes closer than ever to cracking RSA encryption. This is IEEE Spectrum. And he said here, Matthew Green, who's very reputable, you see him on Twitter, he really knows what he's talking about. And he says, anywhere from 15 to 30 years away. But the problem is, we'll get to this in the end. The problem is if you encrypted data, somebody could copy the encrypted data and then try to crack it in 30 years. So it's not okay to use something which is going to be broken in 30 years. And that's the problem. Anyway, so they want a post-quantum algorithm. So there are ways to do it. There are 4 general ways to do it: code-based, lattice, multivariate, and hash-based. And none of these have been proven hardly at all. We're going to see they're all basically in early alpha or beta testing. The math behind them isn't even fixed yet. So we're really kind of shooting in the dark here. Code-based is based on error-correcting codes. Like I talked about before, like we have on CDs and we have on files, we have in, there's CRC32 in Ethernet. Every frame has an error correction. And so that's what this is. There's various forms of error correction code. So this is a encryption scheme with public keys that are 100 kilobytes in size. And it works. So if you want an error correction, if you want to send a 3-bit message over a noisy channel, you could just send every bit 3 times. So the message 010 would be 000, 111, 000. That is one possible way to do it. Now, if 1 bit is wrong, the other 2 bits will outvote it. So if you take the majority of every 3 bits, you can survive a single 1-bit error. And that is like parity. Parity was the original error correction. The reason why ASCII only uses 7 bits is because the 8th bit was used for parity. And you would make it so total number of 1s in every byte is either even or odd. And therefore, if 1 bit was dropped, you could detect that. If 2 bits were dropped, you could not detect that. And this has the same property. If 2 bits are dropped in the same group of 3, you can't detect that. So this has some ability to catch errors, but not if the errors get too common. There are better ones. There's linear codes. So you have a word containing n bits. So treat that as a vector, multiply it by matrix, and now you have a code word. And if you do this, this can detect multi-bit errors if you design it correctly. So the code word is longer than the original word, and it has some extra bits, and you can detect errors this way. So this is McLeish encryption. The secret matrix is made out of 3 other matrices, A, B, and C, and those are your private key. Your public key is G, the product of them, and there is no known way to find these from the public key because you don't have enough information. There are many matrices that could be multiplied together to add up the same G. So you encrypt it by just multiplying the plain text times G and then adding random errors, because the point is it's error correcting. So you can have errors in it and it will clean them out. So if you know A, B, and C, you can reverse this. If you don't know A, B, and C, you can't. And that's the game. G is the public key, A, B, and C are the private keys. That is McLeish encryption. And so this relies on the hardness of decoding a linear code with insufficient information, and that is known to be a very hard problem. So, and even quantum computers can't solve that. So that's the plan here. That's this code-based system, I think. Yeah, they call that the code-based system. This is the hard problem. Taking a combined multiplication of 3 matrices and finding the underlying matrices. That is the hard problem. And that is a really hard problem. So that's one way to go. Next one is lattice-based. This is the one Google's betting on. Google's New Hope, which is the front runner to be the one we're all going to have, is this kind of system. This is a lattice. A lattice is like a field or a group that we talked about before, but what it is a group of elements that are spaced in a multidimensional lattice, like the ions in a crystal, like a salt crystal. So there's some kind of pattern here, and the reason why it's a lattice is there's basis vectors, and here the basis vectors are W and V. So if you start at one point, you go to this point by V, you go to that point by W, and all the other points you can get there by combining an integral multiple of V and W. Somebody hops this way, somebody hops that way, you can get wherever you want to be, and that's what defines the elements of the group. It's also finite. It wraps around with like a modulus, so you have so many things in the group and that's it. And you have a way to combine them. So that's the lattice. And the hard problem, this is one of the hard problems, is the closest vector problem. And the problem is if you choose an arbitrary point, how do you find the lattice point that is closest to it? That's all. That sounds simple, but it turns out to be a hard problem. So, and it turns out to be mathematically identical to 2 other ones. This is the shortest integer solution, which looks very much like the discrete logarithm problem. So if you have a random matrix and a prime number, and you know the random matrix and you know a vector B, you want to find the vector S so that B is A times S mod Q. This is very much like the discrete logarithm problem. What you know is the product of this number and a secret number, and you're trying to basically do division. And that is very hard. And here's another one, which is very close. You do the multiplication, you have the number you know, and the other number you know, and the secret you're looking for, and the connection between them is you multiply one number you know by the secret and then add an error, mod Q, and you get B, and you're trying to figure out what S is. So all of these are very closely related mathematically. That's the fundamental hard problem, like the discrete logarithm problem, which is used in this system. That's lattice-based cryptography. Those problems are kind of confusing. They are believed to be hard, but nobody really knows how hard they are. They don't really know what the right parameters are, and there are a lot of special cases. So this is this seems to be the front runner. But one problem with post-quantum cryptography is just relying on these weird new problems that haven't been researched as much. So even the public key encryption we're using now kind of rests on shaky foundation, and this stuff rests on an even shakier mathematical foundation, but that's where we're at. Then there's multivariate ones, where if you have a system of 4 equations and 4 unknowns, in principle you can solve them. If they were linear equations, it'd be very easy to solve them. But if they're nonlinear equations, these are quadratic equations that have squares and multiplications of these factors. It turns out to be extremely difficult to find those 4 numbers. So if the actual hardness depends on the parameters, if you have a lot of equations, you can choose. Some of these parameters are quite strong, others are not. Some of them have been broken. But that's the fundamental hard problem here. finding the parameters. And the point is, of course, if you know the parameters, like the secret key, you can easily verify the satisfy the equation. If you don't know the parameters, you can't find it. So that's the difference between the public key and the private key. The person who knows the parameters, it has the secret. The person who only knows the equations, but not the parameters, has only the public key. And so that's the game. This has not been used yet. It turns out to be slow and confusing, and nobody's sure how secure it is. But it is another category of problems that quantum computers can't solve either. And the last one is hash-based, which the textbook author says he prefers. This one is actually kind of twisted and insane. I kind of like it. It's very much like password hashes. What you do, he says quantum computers cannot break hash functions because that is breaking a hash function is sorting through lists, just like private key. So all they can do is speed it up by a factor of 2. So if you can crack a 128-bit hash, all you need to do is make a 256-bit hash, and even a quantum computer can't crack it. So you can make a hash function that a quantum computer can't crack, and you can use it to encrypt things with a system like this, watch, one-time signatures. What you want to do, if you want to send a message M, what you do is you take the secret key and you hash it M times with any hash function like SHA-256. And the message is how many rounds you did. So it's easy for you to calculate that comparatively, but nobody can crack it because they can't reverse the hashes. That's the fundamental idea. Your public key is formed by hashing it, this public number, W rounds. That's your public key. And the private key is K, so only someone who knows the private key can do this calculation and figure out how many times you hashed it to get the number you send them, so they can find the value M. So it's pretty cute, and all it relies upon is the fact that you cannot find hash collisions. The problem is signatures can be forged. If I have the hash of one message, I can hash it again to make M+1 and M+2. So I can create more signatures that match real messages. This is the existential forgery attack, which we saw was also true of simple RSA signatures if you don't have proper padding. Another problem with it is you can only use short messages because you have to hash as many times as the longest possible message. So if your message is 8 bits, you have to do 256 rounds of hashing. If your message is 128 bits, you have to do 2 to the 128 rounds of hashing, which is impossible. So you can't send long messages, and you can't use it twice. You have to use a different private key for every message. So this makes it pretty inconvenient.
What happens to the issue where we were saying if you just kept rehashing you with like repetitions?
Yeah, what about it?
You were saying that.
The Pollard row problem.
Right.
Yeah, that actually is another issue. I didn't think of that, but that's absolutely true. Pollard's row might mean that it would be less secure for certain values. Yeah, that's a good point. That probably means you can't just choose anything for the key. He doesn't even brought, but
potential that it would rehash the same.
Yeah, now that you mention it, I wonder if there might be some bad values that lead to short loops. I think there would be, and that would be another problem beyond these. So this thing is pretty lame. This thing is pretty lame. It turns out that the original version of it is super lame, but there are ways to patch some of the holes, which is the same thing is true of RSA signatures. So anyway, that's the game here. So you can make a state-of-the-art scheme which uses more complicated techniques to try to fix these things, and one of them is called Sphinx. And the signatures are dozens of kilobytes long. There are people trying to make these hash-based schemes go, but you do have to patch these holes. And they do get pretty baffling. By the way, if you use the same private key more than once, then it turns out you can do all sorts of evil things. So you can create a whole series of false signatures if that happens. So it's pretty grim. But there are people trying to patch that up. At least quantum computers can't crack it. It has that property, but it has a bunch of other problems that have to be fixed. So anyway, that's where we're at. And so here's the fundamental problem, is the unclear security level. None of these things have been studied enough. We don't really understand what parameters are needed. Most of the mathematical proofs are asymptotic, which means they only show that it gets difficult in the case of really large numbers. But if you really use realistic numbers, it's not really clear how strong that is. And the only way I think you can find out here is to just have more years of people shooting that. That's why banks never want to jump to the new thing. They want to use something that people have been using for 20 years, and they're right, because no matter how brilliant it sounds, you don't really know anything about it until people have really been shooting at it for a while. Somebody will find some way in. Another big issue, of course, is we really have to do this impossible thing of looking into the future. Because if you're encrypting things like medical data today, it is really not okay for it to be cracked in 30 years, and there's no way to protect it. Somebody could steal your cybertext today, and the NSA is totally doing that, archiving all the cybertext in the world in Utah, and they're going to try to crack it in 30 years. And so if you really want them not getting in there, then you have to somehow try to project ahead for decades, and no one knows. All right. And the other issue is, of course, implementation issues. And this is a fundamental law. The first generation of this stuff will make all the usual mistakes. For example, some of these use these ridiculous long keys and complicated calculations, so you try to optimize the code. And if you optimize the code, you become vulnerable to timing attacks, and that has already happened. So, the usual nonsense happens. In practice, any change means the first few generations of code will make all the usual mistakes and be less secure than anything. They'll just make mistakes. It's going to take years to have versions of this stuff that have gotten rid of the usual bugs. Anyway, so that's where we're at. And I got some Cahoots. So let me bring them up. Didn't see any chat messages coming through. Okay, good. Here's the Cahoots. The last Cahoots. Oh, good. I've got the sound. I think I even have a place to put the answers. Okay, good. You might. There's supposedly 10 people online, but they might all be asleep. Apparently not. There's a few people. Yeah.
So has there been algorithms developed for like encryption on computers?
Oh yeah, I'm glad you brought that question up. There's something that wasn't mentioned in your book, but there are 3 related quantum things. I might as well mention them now. We're talking about quantum proof algorithms, which means they aren't broken by a quantum computer. There's another thing called quantum computing where you design things that can only be done on a quantum computer. And people talk about that. I'm not aware of the details, but that's one plan. And the third thing is quantum key distribution, where you use the same old symmetric algorithms, but you distribute the key using quantum properties with photons to have an alternative to Diffie-Hellman. You send the key, and since you send it and it can only be measured once, nobody else saw it. So you don't need any math for the key distribution. Those are 3 uses of quantum that are all completely different. And the only thing we talked about here, which is the most important one in practical terms, is the existing mathematical algorithms and how quantum computers will hurt them. So if you only got 3 people, doesn't really matter, but might as well do it anyway. All right. Some people, this is such is life. All right. So a qubit that might be either 0 or 1. What's that? Okay, that's superposition. Good. Which attack can make AES 128 unsafe? That was Grover's attack. It's the thing that can do this in only 2 to the 64 operations. Which one is based on the CVP? That's the lattice-based thing. That is the closest vector problem, or something like that, where you find the closest point. That's lattice encryption. How about a component that performs computation on qubits? That's a quantum gate. Good. And which attack can break AES 256? None of them. That's the point. AES 256 will survive quantum. Nothing can get in.
Why is that?
Because the fastest known attack is Grover's, and all it does is do it in half the time, in the square root of the time. So it would still take 2 to the 128 calculations even to break this.
Okay.
There's nothing faster. So that's why just doubling the size of the key is enough for symmetric algorithms to survive. All right. And what about McLeish encryption? What did that use? McLeish? I don't know how to pronounce it. That was code-based encryption. And I guess that's it. So surprise, surprise, we have 3 winners. So this is, I know the names of these people. There are, and Dante and Jeff. All right, so I'll send that off. So that's it. The final will be, I think it might be up today by now, or well, up to tomorrow. It'll be up there for a week. I see a chat message. Can I recommend any books about quantum computing for non-physicists? No, I don't know any description better than what you have in this book here. This book is excellent. And, you know, I must say, I don't think it's really important. I would say, I mean, I think the big lesson is it's still in development. We have no idea what's going to happen in development. Things are going to keep changing really fast. So, you know, it's a good question. I do not have a regular recommendation. Looking for some casual summer reading. Yeah, I know the feeling. Quantum mechanics is pretty interesting stuff, but I'm not aware of any easy way to get into it. From a viewpoint of direct practicality, it doesn't really matter. The only thing practically to know is which algorithms are going to be broken and about how long it's going to take. And the answer is the public key systems are all shot, and it'll take about 30 years before that happens. And in about 3 or 4 years, we will have a recommended quantum proof algorithm that we should all start switching to. So will the final be like quizzes? Yeah, the final will be like quizzes, about 4 times as long. You have an hour to do it. It has about 20 questions. And it's multiple choice online, just like quizzes. It's also optional, by the way. All you need is enough points. If you have enough points to have an A without taking the final, you do not need to take it, although you're welcome to. Any other questions? Well, I guess that's it. I'll turn off this thing and put up a video later. Farewell. I'm really glad to have taught this class. I'm really glad to go through this new book, which is really good. I feel like I understand all these things much better than I used to. And this guy is really a champ. I'm hoping to get him to come visit and speak or something. The guy that wrote your book this time actually invented a lot of this stuff. He really is an expert. Anyway, farewell. Oh, I see another chat message coming in. There it is. Okay, good. Agree about the book. Good. Glad to hear it. Okay. Farewell, folks. Have a good summer.